So to keep going here, there are three things to realize about the product, right? If you think about the function we just created, so the linear in green times the red, the parabola, and we expand this equation, so expand h here, it's a cubic, which is, there's a few reasons we know it's a cubic. It's end behavior, the number of zeros, the number of turning points, and so on, consistent with being a cubic. Also, if we expand it, the leading coefficient has a degree of 3. That degree has the following relationship. It is the sum of the degrees of each of the individual functions, right? It makes sense. A linear times a quadratic is going to be degree 1 times degree 2. You're going to add them together to get degree 3, right? That's where we're getting a cubic. The zeros for the combined function are the zeros from each of the two functions being multiplied. Okay, that makes sense, right? Every time that one of the functions is 0, it would drag the other function sort of down with it, right? If one of them 0, it's the other one. Doesn't matter what it is. It's also going to be 0 when you multiply them together. Finally, the domain can only be said to exist where both the functions exist in common, okay? This number 2 is the exact same thing as number 1, so it's very good for you to try this. Do it, see what you get, and then compare it to the note that I posted on the website for today's lesson under 8.2. If you want to do that now, you pause this and go ahead. Otherwise, we're going to go ahead and just look at the last two pieces of information for today, where we are now going to combine more difficult functions together. I would expect for any, linear times quadratic type of question that's well within our range of being able to do, because we know how to deal with polynomials of varying degrees as long as we can factor them. And the nice thing about this kind of work is that they come pre-factored, right? They come in one function times another. So some of the factoring work is already done for you. Like, look at this one. I know it's going to have a 0 at -2. I know it's going to have zeros based on this equation, and then I go from there. This next one is kind of interesting. It's it's sine x and an exponential. What do they look like when they're multiplied together? And this one, there's some good thinking that we need to do in order to kind of figure it out. So let's say, here we're looking at, in green I have 0.75 to the power of x, and in red I have sine x. Now, the first thing I know is that wherever one function equals 0, the combined function is equal to 0. This is very, very important because it's going to help me figure out where to start. So looking at this carefully, if I look at the function, the green function, it doesn't have any zeros, but the red function does, right? It has a 0 here at 2 pi, it has a 0 at negative pi, it has a 0 at 0, it has a 0 at pi, at 2 pi, and 3 pi, and so on. Right? Every k pi it has a 0. Let's just deal with these four. I mean, this should be sufficient for what we need. The other, so far, what do I know? I know my new function has to pass through these 4 points. I also know that wherever one function, well, let's write it like this way. Whenever g is equal to 1, right, f times g is equal to f times 1, which means it's just equal to f. So wherever g is equal to 1, so namely, right here, let's not use f for that, but, let's draw a line. So x equals, so for sine, this is occurring at x. Sorry, whenever I press the button for pi, it seems to be pausing me. For sine is equal to 1 when x is equal to pi over 2, right? So like right there, for example. Also, when x is equal to pi over 2 plus 2 pi, right? One period over, or when it's pi over 2 minus 2 pi. Pi over 2 minus 2 pi. Okay, and just want to draw the line, x equals. There we go. Okay, so we have a few of these different lines here where we can see where the original sine function is equal to 1. If you think about multiplying, right, let's get rid of the axis just to make this a bit easier for us for a second. If we think about multiplying things, if you multiply a number by 1, then the number is whatever it was before. Therefore, whenever one of the functions is equal to 1, the value of the combined function is simply equal to the other function. That's what I'm trying to say here. F times g is like saying f times 1, and f times 1 is just f. So that tells me wherever sine is equal to 1, my function is equal to wherever the green function is at that time. Okay, and that's why I draw on these points f and g and h. Okay. From here, okay, we can kind of get the idea that I'll just use this tool to try to draw this one. We can now see how this is going to have to pass through all the points. So what I'm going to do here is I'm going to get rid of these 3 lines, and I'm going to get rid of the 2 functions. Actually, I'll keep the 2 functions. And let's just draw what we can draw that passes through all these points. And it might seem complicated, but it's not going to be that tricky. So we're going to draw. It has to pass through all these zeros, and it has to pass through this point. So to do this, what we're going to do is it's going to come up, and then it's going to come down, and then it's going to come up, and then down, and then up. And so what we're kind of getting here is an exponential function that is decreasing in an exponential, or sine function rather, is decreasing in an exponential way. Let's actually have the computer draw this because it'll be a much better job than what I did. And you can see it comes up through all these zeros, and it passes through all these special points when sine was equal to 1. And so if we zoom out on this a little bit, you can kind of get a better sense of it. It's a wave that kind of shrinks and decays in an exponential way over time, right? And so that's the kind of main idea, the last idea that we're going to use today, where we're going to use 2 techniques in order to graph this properly. Number 1, wherever either function has an x-intercept, the combined function has an x-intercept. Okay, the second thing is wherever g is equal to 1, f times g is equal to f. Wherever f is equal to 1, f times g is equal to g. Okay, you can expand this if you want. You can say wherever g is equal to -1, f times g is equal to -f, right? So it's like it's flipped over. But really, if you just remember these 2, well, I guess these 3, that's sufficient to enable us to be able to draw this function. And like I say, it's kind of like a wave that has, if we just get rid of all these points, you kind of see it a bit better, that has exponential decay in it, right? The amplitude of the wave is decaying in an exponential way over time, right? And that's the kind of picture that you get. And it's consistent sort of with the exponential function rising in that manner. So with that in mind, I think the best thing for you to do is to actually try these questions on the last page. Try to reason out to yourself, let's try. I'm going to do the first one, and I want you to do the other 2. Obviously, you can match them, and I'm sure you can use a graphing calculator and figure out which one's which, but I want you to concentrate on the thinking behind how do you identify each one. Let's say I'm looking at this combined function, and I notice that this combined function, h of x, is odd. This means that h of x is equal to f of x times g of x, and f of x and g of x must be different. So either odd even or even odd. Because if the combined function is odd, it means that the 2 functions that make it up have to be different, right? So, based on that, you can use that to eliminate from the top three which one it has to be, right? But let's say we didn't have that and we had to figure this out ourselves. I notice that the combined function h of x has zeros at it has a zero here at 1.57, 1.57, which I know is actually pi over 2. It has another zero here at 4.5, right? 4.6, which is at 3 pi over 2. And it has zeros over here at the same places, right? So again, I'm noticing that h of x has zeros wherever cos x has zeros, right? Which tells me that cos x is part of the equation. I also notice that h of x has a zero at 0, which cos x doesn't have. This 0 must come from the other function. Okay, this is very important. So we're looking at this and we're going, it has a 0, the same place cos has a 0. So cos is part of the equation. It also has a 0 at 0 itself, which means the other part of the equation has to be giving it that 0, right? This has to be explaining where that's coming from. I know that cos has a maximum at of 1 at 2 pi, which means that if you look at this function around 6.28, that is where the function must pass through, which means that this function, that the other function passes through the same point as the combined function. So I'm going to conclude that this must be x cos of x. And let's just briefly kind of look at the diagram of x cos of x, and then I'll let you try the other two. So suppose we're looking at this, and I'm looking at x cos of x, and it is the exact shape that we wanted, right? It's this odd symmetry where it's up to the side on the right and down lower on the left. And again, if I graph cos x, you'll see that cos x shares a 0 with this function every single place except right here in the middle. This is where the other function comes in and it provides the 0 there. Okay, so these two functions, cos and this line x, combine to make x cos of x. And if you look, wherever cos is at a maximum, so for example here at x equals 2 pi, you can see that the function, the combined function in orange, passes through the function h, because like I said, if h times cos and where cos is equal to 1, then it's like h times 1, right? The combined function is just the same. So you can kind of use this method of noticing that the line touches all the crests on the right side and all the troughs on the left side. We can kind of use those kind of ideas to help us. I want you to try the other two and then look at my answers. And again, if you have any questions about these ones, please bring them up tomorrow. Okay, feel free to post questions to the site, and we'll talk about division tomorrow, which will help us kind of go over some of these issues from multiplication as well.